Good morning. Selecting a smoke detector isn't a catalog decision, it's an engineering decision. You are evaluating plume and ceiling jet flows, ambient temperature and humidity, ceiling shape and structure, surface, ceiling height, fuel type and configuration, HVAC flows, stratification potential, installation requirements, and the detector's own capabilities. If you miss one of these, you can install a perfectly listed device that still doesn't activate in time. I want you thinking like a fire protection engineer here, not just a code checker. Every one of these factors changes where smoke actually goes. This standard is, of course, this training is not a design training, but just this section may a little bit require you to act like a designer. For ceilings up to 40 feet, absent performance-based design, you have two paths. Option 1, detectors no more than 30 feet apart nominal, plus detectors within half that spacing from walls extending into the top 15% of ceiling height. Option 2, every point on the ceiling within 0.7 times the 30-foot spacing, that is your radius method. Notice NFPA's own research foundation study on high ceiling spacing sits right behind this rule. This isn't arbitrary. It is tested, science translated into a prescriptive number you can apply in the field. Okay. This diagram is the why behind everything we are about to cover. Smoke rises as a plume, but it doesn't always reach the ceiling. It can stall in a hot air layer and may spread laterally, never touching your ceiling mounted detector. That's called stratification. Look at the exhaust fan on top, pulling that layer sideways. The note tells you the fix, the beam detectors, projected below the ceiling at the stratification level, can catch smoke that a spot detector at the ceiling would completely miss. Keep this image in mind for every atrium and high bay space you inspect or you discuss. Okay, now we have obviously a video on our slide. This is a real test footage, not a diagram. Watch how the smoke plume rises, expands, and essentially stops climbing at a certain height, spreading horizontally instead of continuing to the ceiling. This is exactly what a thermal boundary does in a real building. If your detector is above that stratification layer, it is not seeing smoke, that means, at all until conditions change dramatically. This is why install detectors on the ceiling is not a universal answer. Height and thermal conditions dictate whether ceiling mounted detection even works. Okay. Here is the multi-floor cross section of a building, fire at the base, plume rising, but see that red no entry symbol at the roof level? That's telling you don't rely on roof level detection alone in a tall atrium space, because stratification can prevent smoke from ever reaching that top layer. The open floors on either side represent the kind of atrium or lobby geometry where this becomes a real design challenge. You need detection at intermediate levels, not just at the highest point. Now follow the smoke path. It rises from from the fire hits a thermal layer partway up and travels laterally into the adjacent floor opening instead of continuing toward the roof. The S markers show detectors positioned at each intermediate level, which is the design response to what we just saw in previous slide. This is the practical takeaway. In open, multi-story spaces, you often need detection at multiple elevations, not a single line of detectors at the highest ceiling, because that's exactly where the smoke may never arrive. Here is a real atrium. Notice the two arrows pointing detectors mounted at different elevations along that sloped ceiling. This is a design team applying exactly the principle that we just discussed. Multiple detection points at different heights to catch smoke wherever stratification happens to occur. When you are field verifying a system like this, don't just count number of detectors. Check whether their elevations actually corresponds to where the engineering analysis says stratification is likely. This is another example, a convention center concourse. It's a great real-world case. Tall, open, high traffic, and architecturally complex with that curved roof structure. Spaces like this are exactly where you cannot rely on textbook spacing tables alone. The ceiling height, the roof shape, the HVAC design all interact to determine where smoke will actually stratify. This is where performance-based design and engineering judgment take over from the simple prescriptive tables, and where you as the AHJ or designer need to ask for supporting documentation. Think carefully before you answer this one. Table 17635.1 can be used to correct smoke detector spacing for height. Is it true or false? Okay, but does it correct for ceiling height, or does it correct for something else entirely, like sloped or peaked ceilings? A lot of people conflate every correction table in this chapter as being about height. They are not interchangeable. Vote now in the voting buttons, and then I'll walk you through exactly what that table actually governs, and where the real height correction guidance lives instead. Spot type on smooth ceilings. This is your classic radius of coverage layout. Each detector covers a circular area with radius r, and the circles overlap to guarantee full covering of the ceiling, no gaps at the corners. Okay. If your nominal spacing is SD is 30 feet, work out R with me. It is not simply 30 feet because the coverage circle has to account for the diagonal distance between detectors. This geometry is exactly why half spacing appears along the walls. You are covering the full square footage, not just placing detectors on a grid or hoping. Corridors get their own spacing allowance under A1763.1.1 E. Up to 30 feet between detectors along the direction of travel, with a 15-foot maximum from a detector to the end wall and 15 feet of coverage width. This works because a corridor concentrates the smoke movement along a linear path. You don't need the same two-dimensional radius coverage you would use in an open room. This is a very common inspection finding. Corridors laid out using open area spacing instead of taking advantage of this more efficient corridor allowance. Okay, this is allowance. Quick chat question before we move on the second corridor example. If your nominal detector spacing is 30 feet, what is your actual allowable design spacing once you apply the appropriate reduction or correction factor? This connects directly back to what that radius calculation of from 2 slides ago. Type your answer in chat. I want you comfortable converting nominal and spacing into real design spacing, because that's the number that actually goes on your shop drawings and gets field verified. Here is the corridor rule scaled up: 20 feet of coverage width, 40 feet of overlap, and length between detector zones, and that 21-foot maximum distance from the detector to the end of the corridor. Compare this to the previous 1530 example. The numbers shift slightly depending on which specific corridor allowance and addition detail you are applying. This is exactly the kind of detail where I tell my teammates, don't memorize one number, memorize the method, then verify against the current table every time. Joists and beams change how smoke moves along a ceiling. They create pockets that can trap or channel smoke laterally before it reaches the detector. The first rule: if beam or joist depth is less than 10% of the ceiling height, that's shallow enough that you treat the ceiling as smooth and just use your normal smooth ceiling spacing, SD. No pocket by pocket calculation needed. This threshold, that 10% number, is the gateway test you apply before deciding which of more complex beam rules even matters. Now we see a photo, ceiling photo. This makes the point concrete. Shallow wood joists and the smoke detector sitting directly beneath, unaffected by any meaningful pocket depth. Since beam depth here is clearly under 10% of the ceiling height, this installer correctly applied ordinary smooth ceiling spacing rather than treating each bay as its own pocket. When you are in the field and see joists like this, your first move is always the same: measure the depth to height ratio before you even think about pocket by pocket placement. So that's we need to take care about. Okay, now the deeper beam scenario, when the depth is 0.1 h or greater, or 10% or greater, the beam spacing is 0.4 of the height, 40% of the height or greater. Each pocket between beams effectively becomes its own smoke reservoir. The rule: one detector in each and every pocket, no skipping bays. This is where I see the most missed detectors in the field. Installers running detectors down the center line of beamed ceiling without realizing every single pocket needs its own coverage, once depth and spacing cross these thresholds. Okay, there's a slightly different condition here. Depth still at least 10%, but the beam spacing is now less than 40%, meaning the beams are closer together. In this case, you don't need a detector in every single pocket. Instead, your design spacing perpendicular to the beams becomes half your normal smooth ceiling spacing. The logic is that closely spaced, shallowish pockets behave more like a slightly rougher smooth ceiling than like isolated reservoirs. So the code lets you to use modified spacing instead of one detector per packet. Waffle ceilings are the two-directional version of the beam problem. Packets running both ways, like an actual waffle. The rule here is to treat each direction separately, applying the appropriate beam and joist reduction along each axis independently, then combine the results. Don't try to shortcut this with a single spacing number in both directions. The geometry genuinely differs from a simple one-way beam ceiling. Treating it as such protects this space. Okay. The good news for narrow corridors: if the corridor is 15 feet wide or less, even with beams or joists present, you are allowed to use standard smooth ceiling spacing (SD) along the corridor length. The reasoning connects back to what we covered earlier. A narrow corridor already concentrates smoke flow linearly, so the added complexity of pocket by pocket beam analysis isn't necessary. This is a genuine relief provision. Don't over-engineer a narrow beamed corridor when the code already gives you a simpler path. And the last exception and last slide we will cover today is in the set rooms smaller than 900 square feet with joists or beams still get to use standard smooth ceiling spacing. Regardless of the beam depth and spacing rules we just went through, the room's small footprint limits how far smoke can travel and before hitting a detector anyway. So the pocket trapping concern that drives the other rules becomes less significant. Always check square footage first on small beamed rooms. It can be also saving you from unnecessarily complex detector layout. Thank you for your interest for today's training.